Today we are going to see certain operations on binary search tree. Operations like searching an element in BST. We will find the location of some specific elements in the binary search tree, and then insertion in binary search tree. If you want to add new element to binary search tree at appropriate location, okay, so that it won't violate the property of BST, and deletion in BST. We will see the implementation of all different operations in Python. Hello everyone, this is Sharda from Go Edu Hub Technologies, and today I am going to tell you about Bst operations. In the last class we already seen what is the binary search tree, and we have created binary search tree. Okay, and we were in between of implementation of search. So today we will complete implementation of search, and we will see the traversal, and then we will see the deletion of an element in a BST. Guys, can you please confirm me, am I audible clear? You can write in the chat window, am I audible or not? Okay, so that we can continue for the class. Meanwhile, I'll tell you, like, first of all of you know that what is the binary search tree. Binary search tree having certain like it can have at most 2 children's, and left children value always small than the root, and right children value is always greater than the root. Okay, so basically now we will see the implementation. We know how we can we can add an element in the binary search tree. Like I can tell you here, I can take a tree BST, okay, and then I just want to add certain elements. Okay, I just want to add certain elements in a node. So suppose I just want to create a binary search tree, and I'm taking certain values like 43, and then you can say 10, then you can say 79, you can say 90, you can say 12, or some 54, something like this. So what we will do, we will make first value as a root node. So here I'll write 43 in the step 1. Then we will go to the second element, and then we will check either this element is greater than to the root or less than to the root. So it is the less than to the root, so we will add this element in the left side. Similarly, we will search for the third element 79. 79 is greater than root, so we will add this at right side. Okay, and then we will see here 90, you can see 90. 90 is greater than the root. Okay, so we will go in the right side, and in the right side we have already one element, that is the 79. So we compare this 90 with the 79, and we will check it is greater than 79, so we add this element at the right side. Similarly for the 12, we will check 12 is less than the root, so we go in the left side, and there is one more element 10, so 12 is greater than 10, so it will append in the right side of the 10. Similarly for the 54, 54 is greater than the root, so we will go in the right side, and in the right side we will check out for the 79. 79 is greater than 54. Okay, 79 is greater than 54, and there is no child in the left side, so we will add here 54. So we create the tree like this. This is for insertion operation, or you can say creation of a binary search tree. So we will do the implementation, Python implementation of insertion, and then searching. You just want to search out an element. Yesterday I already told you mechanism of searching. So we will search an element in binary search tree. Same technique we will apply. We check either element in the left side or left half, or in the right half. Okay, so search operations, we find the location of specific elements. So we compare the element with the root, and then we will check if element is greater than the root, then we will go in the right side, otherwise we will go in the left side, and same technique we will apply to all subtrees of this tree. So this we will do the implementation in the Python. And third thing is deletion. Okay, this is little bit different. Like in the deletion there would be more conditions. Like deletion, you can delete a node, either it is a leaf node, there can be certain condition. You just want to delete, like you just want to delete 12. This is a leaf node, you can directly delete this element. It won't affect. Or if you want to delete 10, then a node having one child. Okay, so second condition is a node having one child. One child. Okay, and third condition is a node, like I just want to delete 79. So I just want to delete 79. That case 79 having two childs. Okay, so I can say here I just want to delete 12. Either I just want to 12 means it's not only the 12. 12 means leaf nodes. Okay, 12 either 54 or 90. And I just want to delete 10, the node which have only one child. And I just want to delete the 79, the node which have two childs. Okay. So there is the different ways. This is the simplest way. You can delete directly. There is no more worries. You don't need to worry about all other things. You can delete directly. But in the case of having one child and two childs, we need to take care of childs. Like here, I just want to delete 10. Then what we can do? We will delete this node, and in place of 10, we have to put this value 12. So what we can do? We can copy its child. Okay, and it's a child value we will put here, and then we will eliminate the child. And like there is two childs, in this case what we can do? There are the two ways. You can pick the maximum value of the left side, or you can pick the minimum value of right side. Okay, we will see that. When we will do the deletion, you can understand that. Okay, so let me start the implementation part, how we can do the implementation in the Python. Okay. Yeah, I got certain questions like where is the assignment of yesterday's class? Okay, Somme, actually we were not posted yesterday. Today you will get the assignment of last class. Okay, so today you will get the assignment of last class and today's class as well. Okay, so let me start the implementation part. There was some technical issue, that's why we not posted yesterday. There was some problem in my system, so that was some issue. That's why I have left the class in between. Okay. Yeah, good evening to all of you. So just open your Google Colab and we will do the implementation now. Okay. So let me write the quickly code. I'll create a binary search tree. Okay. So here the class I'm going to write binary search tree. Today we will see all three operations: insertion, deletion, and creating a binary search tree. Okay. So this is the class, and inside this class I am defining a constructor, a function in it to create the nodes. Okay, so here I am writing self, that you already know, self comma data, and your tree can have two childs at max. So what we can write, self.data, that is the value for the node, that is data. And one child I'm keeping self.left equals to none. And one child we are keeping self.right equals to none. Okay, and then we will define one more method, that is the add childs. Okay, add child, and inside this I'll write the values self and data. And then what the conditions, either node already, one property of the binary search tree is it cannot have duplicate values. So a value which you want to add to the tree, that can be already present. So for this case, we return empty. So here I'm writing node already exists. We are creating a binary search tree. Okay, so we just want to add the childs to the root node. So first case, what we can consider, if element, that value, like here we have taken the example 43. 43 is root node. After the 43, I just want to add here can be 43 again. So I just want to add the 43, but 43 is already present, so I'll remove it. Okay, so this condition I'm writing here, if self.data data equals to self.data. Okay, in this condition I'll return empty. Okay, second condition can be like I just want to add a value, add an element, and that element can be added at the left side or either the right side. So I need to check out. Okay, so first condition can be my value is greater than the root node. If value is greater than root node, then what we will do? We will go in the right side. And if value is less than the root node, then we will go in the left side. What is the value? This data. So first I'll go in the left side. So here I'll write a condition data. If data is less than self.data. Okay, I'm traversing left side. And in the left side, what I can do? There can be more elements already present in the left side. So what I can do, I have to check all the left elements. So until there is the left element is available. So self.left. Okay. So for this, what I will do, recursively I'll call self.left. With the help of self.left, I'll call add child. Okay. And here I'm putting value data. Okay, and other condition can be like else. This is traversing. Okay, in the else condition, I'm adding the node to the left side. Okay, so here self.left equals to binary search. Binary search tree node. And then I'm writing here data. Okay. So in this case, whatever the data we are adding to the left side. And in the if condition, what we are doing, we recursively reaching to the last left node. Okay. So at the last left node, we will add the data value. Okay. And other side, else condition, like for the right side. I just want to traverse for the right side. Right subtree. Right child. Or here left child, adding element to the left child. Okay? Getting? In the else condition, we will write the same thing. If we traverse all the right, and then self dot write recursively we will call add child. Okay, data, and in the else condition I'll write here self dot write equals to binary search tree. Okay, getting the things? This is, I can add the elements in the binary search tree. Okay? How can we mark it as present? Basically, we are starting. Like in the starting, by default, the present thing is by marking by the help of the self. Like current object. Initially, it will create, this constructor will execute and self.data equals to data. So whatever we are having for first node, I'll write one condition here. Okay. Diagram manner I have already told you, Mani. Actually in the diagram I told you, like here I have created this diagram. I have certain values like 43, 10, 79, 90, 12 and 54. I just want to create a tree with the help of these values. So what I'm doing, the first node I'm taking as a root node, that is the 43. After this, I just want to add this value 10. Okay. So what I will check either 10 is greater than 43 or less than 43. So 10 is less than 43. That's why I have added 10 as a left child. After this, I'll go to the next element, that is the 79. 79 again I'll check either it is greater than the root or less than the root. Okay. So it is, my current is root. So it is greater than root, so I'll go in the right side and I'll append this 79. Then again there is one element, that is 90. I'll compare 90 with this root element. And this root element is 43 and 90 is greater than 43. So I'll come in the right side. In the right side I have already 79. So I'll compare again 90 with the 79. Okay. So 90 is greater than 79. So this will go in the right side of the 79. Again we will take the 12. 12 is less than the root node. Okay. Then we will go in the left side, and in the left side there is already 10 present. We will compare 12 with the 10. All the process, whatever we are applying to this root node, we have to apply to all the sub trees. Okay. So we will take 12 is greater than 10 and there is no right child, so we will add 12 to the 10. Similarly for the 54 initially we will compare 54 with the 43, and if 54 is greater than 43 we will come in the right side we already have 79 and 90, so we compare with the 79, 54 is less than 79. So we will take in the left side there is no child, so we will add 54 in the left side. Hope you got the thing. Okay. So this is the diagrammatic way how you can create a BST, and that is I have written in the Python code in add_child. I made the 3 conditions. Like first condition, and if element is already existing, that I need to take care the binary search tree keeping only the unique values. Okay. And left child, we are adding in the left child. Okay. Like we have to reach till, that's why I have called this add child recursively. I need to take care of all the subtrees of this tree. Okay. this is how you can create the tree. We will see its output also. Okay, don't worry about it. Next thing is I can apply either the search operation or like I have to build the tree. I just want to see the output, so I have to define one more function. That is the build tree. Outside this class, I'm defining one function, build tree. Outside this class, okay? So build underscore tree. And inside this, I'm keeping all the values, okay? Values. And then values, how can I add the values? Here I'll print building tree with these values. Okay, and what are the values I'm picking here? I'll take a list. Like I just want to create certain tree from a list of values. Okay, and here okay, and I have to define the root. So root equals to binary search tree okay, and I'll define the root as a first element of this list. This values is a list of items, list of values. This is a list. We are passing in this function a list, like certain values. Okay. When we will call this function, we will pass here a list. So first element of this list. So values of 0. I'm making root. And then here I'm writing a loop for I in, like from the next element. Range 1 comma length of values. Okay. And here I'm writing root dot add child. I'm calling this function with the help of root. Values of I. Okay, this is for creating, and at the end what I will return here in the function, I'll return root. Okay, now I'll call this function like entry point. Execution starts from here. Okay, in the execution what I will do, I will basically create a list. So values equals to, I can take any values, like I can take some numerical values as well as I can take the list. So here I can take the numerical values as well as some string values, list of string values. So here I'm picking some string numerical values like 17, 4, 1, 20, 9, 23, 18 and 34. I'm picking certain values. Okay. And you just want to see the visualization, then you have to write one more function for printing a tree, or either you can write a function for traversing a tree, because a build tree won't give you an output. Okay, it's not printing, it's simply printing it values only. Okay, so we will write one more function for traversing, or we can write a function for searching the elements. Then we will test this all these functions. Okay, so I'll define one more function for in order traversing. Def in order, you know what is the in order? In order, I already told you in the last class. In order, first we will traverse left child, then we will traverse the right side, root and then right side. Okay, like for this tree, okay, like I have taken one example, and for this tree, in-order traversal. What is the in-order traversal for this tree is, in-order traversal is first I need to traverse left child. So I'll go from here, root to left is 10, and on the left of 10 there is no element. So I'll pick this 10, okay, and then right side of this is 12. So left child of this 43 is traverse, and then we will pick here 43, and then we will come to the right side. Again at the 79 we will follow the same rule. First we will traverse the left child, that is the 54, and then root 79 and then the child. So this is the output of in-order traversal. Okay. So here we're defining one more function for the traversing. Okay, inside this I'm not passing anything, so I'm just writing here self. Inside the class I have written this function. Okay, and here I'm taking values equals to empty, an empty list I'm taking, and then I'm taking if, like two things I have to check, left child and right child. So self dot left, I'll traverse first left, and in the left what I will do, I'll add the values to this list. So values plus equals, I'll add values to the values, self dot left, and here recursively I'll call in order traversal. Okay. And outside this condition, I'll add the element, whatever the element we are having. So values dot append, okay, and here we will write self dot data. Like this is this condition, this if condition only for traversing. And we are adding the left childs. Okay, and same thing we can do for the right also. If self dot right until we have right child. So what we will do, values plus equals self dot right dot in order. Okay, and at the end what we will return? We will return values. Okay, and we can print the values, so it will give you a in order tree. So here what we will do, for we can build a tree and we can traverse a tree. So first I'll traverse a tree. For traversing I have to build a tree, right? So tree equals to build underscore tree. I'll call this function build tree, and inside the build I'm calling add child. Okay, so build a tree, and inside this I'm passing values, this list. For this list, I just want to create a tree, a binary tree, a binary search tree. Okay? And after this, I just want to print in order traversal of this tree. Okay, and here I'll write like tree. Okay, tree dot because this tree is what we are getting in this tree. We are getting the root node. It's returning you to the root, and we are creating a tree inside this. So we are creating an object of this binary search tree node. And this binary search tree node object, with the help of this object, we can call the functions of this class. And one of them is in order traversal. Okay, so tree dot in order underscore traversal. Okay, let me run this code. Hopefully this will execute. Okay, there is certain syntax errors. Let me correct. Here I need to write 1. Okay, just try to understand this. Okay, what happens here, the values, this is my list. Okay, I'll tell you how it starts execution. First, this is the list. Okay, and with the help of this list, we are calling our build tree function. This is the simple Python function, build tree. And above the build tree, I have created a class. Okay, binary search tree node. Inside this class, I have certain functions. One is the init, one is the add child, and one is the in order traversal. Okay, I have 3 functions, and my class name is binary search tree node. And outside this class, I have defined a function build tree. And inside this build tree, I'm creating an object of binary search tree node. Okay, and then calling a function of this binary search tree node, that is the add child. And at the end, I'm returning root. Okay, yeah, just wait, I'll explain you in order traversal code part. Okay, just wait, just try to listen me. I'm telling you what's happening here. Start execution, how it executes. Values are this, build tree, it will create a tree and it will give you the root node. Okay, and with the help of this root object, okay, you are calling in order traversal. And in order traversal of this tree, okay, is shorted output. Like we will create a tree diagram. We'll see first the diagram of these values. Okay. I'll take the same values here. Okay. Like 17, 4, 1 and 20 and then 9 and then 23 and then 8 and then 34. I have list of values. Okay, tree which I am constructing from these values are like this. Initially 17 as a root. Then 4 comes, it will take, 4 is less than the data root node, so it will go in the left side. Then again 1 comes, 1 checking, 1 is less than the root, it will go in the left side. There is one more element 4, again we will compare with the 4, 1 is less than 4, it will go in the left side of 4. Then 20 comes, 20 checks, 20 is greater than root node, so we will append 20 in the right side. Okay, and then 9 we are checking from the root node, it's less than, so we are going in the left side, and then the 4, it's a greater than the 4, then we will go in the right side, and there is no element, so we will add 9 here. Then come to the 23. 23 is greater than the 20. Okay, so what we will do, we will take from 17, it's greater than 17, we will come to this, again we will take it's greater than 20, 17 and then greater than 20, so we will append in the right side. Similarly for the 8 comes here, it go in the left side, greater than this and less than this, so it will go here. And then 34 we will take here, here and here, and then 34 will go here, something like this. Now in order traversal, what happens in the in order traversal, we will first traverse left child and then we will traverse right child. What the concept of in order? Left child and then root and then right child. Okay, so what we will see here, go to the root node. Okay, we will take either it have left child or right child. Left child we will go in the left because we first need to traverse left child, so we will go in the left. Okay, and again from this element we will take left and right. We have left, so we reach to the leaf node, that is the 1, so we write here 1. And now we traverse the left side of this tree. This is a subtree. Okay, so for this subtree we traverse left child. Now we will traverse root, that is the 4. Okay, and again we will come to the right side, and in the right side there is one more elements, more childs, so again we will follow the same concept. For this tree, this is the subtree. For this subtree we will traverse first left and then root then right. So first we will write here 8 and then 9. Now this part is completed. Okay, and this complete subtree, left subtree is completed, so we will write here root, that is the 17. Now come back to here in the right side, again we will follow the same concept. In the right side subtree, first left child then root then right child. So for this we don't have left child, so left child is null, so we will traverse root is 20, so we write here 20. And again we will come to here in the right side we have 23, there is no left, so we traverse the root, that is the 23, and then for this we will traverse the right side, and this is the leaf node, so we will write it as it is. And you can see the output is in the shorted order. Okay, this is the in order traversal. Now come back to the code part. I'll explain you one more time what is the in order traversal code, what we are doing here. Okay, this is the output you are getting. In order traversal code, we'll come back. We are taking a empty list. Okay, you can print here values, so you will get the more ideas. Left side. Okay, values. What is this? First in the left side is 1, then 8, and then 1, 4, 8, 9, something like this. So left childs are 1, 8, 1, 4, 8, 9. Left side childs are 1, 4, 8, 9. Similarly, right side childs are 20, 23 and 34. Okay, now come back here. What happens here? For the, we have two conditions, like left child and in the right child. And this is the outside this. Okay. For the left child, we will recursively call in order. Okay, so here values, we are assigning the values. Okay, values equals to values, and with the help of this left child we will go in order traverse. Again we will go in the left child until we got the leaf node, and whenever we are getting the leaf node we are adding that to the values. Okay, and like whatever the current data we are appending to the values, and same thing we are doing in the right side. This is for the root node here. This values dot append we have written for the root node. Like first we will traverse this left child. We add the left child values to the values. And then we have to add the root node value. So when we complete the left child, like recursively we have called the left child. So we completed the left child. That time we reach to the current root node. So the data we having in the root node we will append to the values. Okay, and similarly for the right side. And at the end we are returning values. I hope you got it. Nirmal and Mani. Okay, so like this we can add the elements, we can insert the element in the binary search tree, and we can do the traversing of binary search tree. Now the next thing is we will do is searching operation and then deleting. Okay, search is simple. For the search, what we can do? Search is we just want to find out either element is present. If it is present, we will return true. Otherwise, we will return false. Okay, like I just want to search out here 17. Okay, sorry, 17 is root. So in place of 17, I'm picking here 23. I just want to search out 23. For this, what we will apply the same concept. First we will compare with the root node, then we will decide either I have to go in the left side or I have to go in the right side. Okay, and similar process we will apply for all the subtrees of this root node. Okay, so let me write the code here, you will got clear idea. Okay, I'll write one more function, search function. Okay, inside this class I'll write one more function, search. That is pretty simple. Def search, and I just want to search a value. So here I have to pass a parameter called value. One value I just want to search, or you can write here data I have already taken. So I'll write here value. Okay, so first condition, if you are lucky and you are getting the value at the root node, then what happens, what the code we will write simple, self.data equals to value. Then we will okay, and then we will return true. The value which I am searching is root node value. Okay, this is one condition. Another condition is value can be less than the root node and value can be greater than the root node. So I have to decide in which direction I have to go. Okay, if value is less than, okay, value is less than self.data, and here I'll write if self.left, okay, like I have to go in the left side. If my value is less than the root node, then I have to go in the left side. So there is two conditions. One is like element is present, otherwise I can say if I'll traverse all the left nodes and there is element is not present in tree. So I have to write two conditions. First is until left element is available. So I'll return self dot left dot, recursively I'll call the search value. Okay, and in the else case I'll return false, means element not present in the left subtree, means element not present in the tree. Okay, this is one case. Same thing I have to write for the right side also. If value is greater than self, guys, after the class just try to implement all these things. If you write the code by your hands, then you will get a more clear idea. It's nothing like, it's not you are attending the class and you will get each and everything. When you will do the practice, then only you will understand each and everything. Just imagine how recursion works, how I'm calling the things recursively. Like before the binary before this class, before last class, I have taken one class for the recursion, because recursion is most important when you are studying the trees. In trees we always apply the recursion, and it's easy way. Okay, but when you will do 2-3 examples, you will get the clear idea of recursion. Recursion is nothing, I don't need to write the more code, it's a simple. I'll just calling this function. Okay, so value dot self dot data, then here if self dot write, okay, and here I'm returning what I need to write here, self dot write dot search value. Okay, else element not present, return false. Okay, this is the search function. Now let me run the search function. We will try how this will work. Okay, here this is, I need to change some settings. Okay, traversal we have tested. Okay, and we have created a tree called tree equals to build underscore tree values. Okay, now this tree I'll use the search function. So print, okay, like 23 is in list or not. Okay, I'm checking 23 is in list. So what I will write here, I'll write here tree dot search. Okay, and inside the braces I have to pass the value 23. Okay, let me run this. It's a true. In place of 23, now I'll write 230. And you can see the output, 230 is not present in the list. Okay, are you getting the things? Basically what I'm doing here, I'm just searching for an element, and same conditions I'm writing here. Bst is pretty simple. You just understand one concept, that is the how we can write the code for the left child, right child, whatever we are applying to the root node, we have to apply to all the subtrees. Okay, guys, can you please give me a quick confirmation? Are you getting the things? Or if you have any question till now, you can ask me. Otherwise, I'll ask a question. Okay, like I just want to find out the maximum element of the tree. How can I get? Or minimum element of a tree. Okay, just think about it. find minimum element in this binary tree or maximum element, or you can calculate the sum of all the elements. You can perform post-order traversal of a tree or pre-order traversal of a tree. So that you have to do by yourself, pre-order and post-order. Concept you know. For the pre-order, what we are doing, let me tell you one more time. Like we have done in order. Okay. Now if we do pre-order and post-order, for the pre-order what we can do, first we will visit root and then left child and then right child. And for post order, what we will do, we will first left child, then right child and then root. Basically order of left and right is same. Always we traverse left first then right. But the order of root is changing. Here in the in order root is in between, and in pre-order root is first, and in post order root is the last. Okay, and I just want to get the minimum element. Then how can I get the minimum element of this tree? You can say the leftmost element having the minimum value. Okay, so in the left side, when left leaf node, when left is empty, then we will return the value, and this value is minimum. And similarly for the maximum, when right is null, like after this there is no right, so this is the maximum element. Okay, and I just want to calculate the sum of all the elements. So what I can do, I just have to add left child, right child and root values. Just give it a try. Okay, let me tell you about the another operation, that is the delete. I hope you will do this. Okay, so now I'll tell you one more operation, that is the deletion. How you can perform deletion? You just want to delete an element in binary search tree. So there are the certain conditions for the deletion. Let me explain you first. Okay, delete element in Bst. Here there is three possible conditions. Okay, like I have told you, first is the node which you want to delete is a leaf node. Node to be deleted is leaf node. Then you don't need to worry about it. Like simple case, you replace the leaf node with the null. Okay, we simply delete the leaf node, we don't need to worry about it. Okay, remove the leaf node. Like here I'm creating a tree, suppose 50 and then 25, and here I'm writing 75. Okay, and then here I'm writing 12 and then 30. Okay, and here I'm writing 60, 85, and then you can say 52. Okay, now I just want to delete 85. I can delete easily. I can replace this with the null. Okay, this is the simple case. Second case is the node which we want to delete is having only one child. Okay, like I just want to delete 60. In case of 60, I just want to delete 60. And what we will do, it's little bit complex. Like what we are doing here, we need to check out its leaf and then we put the leaf value here and then we free this. Okay? So we will replace this 60 with the 52 and then we remove the leaf node. So replace with its child and then delete child. Simple. The third case is we want to delete an element that having two nodes. Like you can say 25. I just want to delete the 25. It having two childs, left and right. Okay? This is little bit complex. Means node to be deleted, it can be replaced by its left child or right child. Either you can say there is one more value like 6. Okay? So we can replace this 25 with left successor or right successor. Okay? So what we can do, we can check the minimum, we can pick the minimum of right tree or we can pick maximum of left tree. Okay? So maximum here, I'll put one more value like 13. Okay? So if I'll go to in the left side, then the maximum of left side is 13. So I'll replace this 25 with 30. One way. Another way is maximum of right side. Maximum of left side and minimum of right side. So minimum of right side is like if we have some value here 24. So minimum of left side is 24. We will replace this 25 with 24 and we will delete this element. Okay? So two ways we can create the tree. Okay? So let me write the code how we can delete an element in binary search tree. We will write the code. Okay? Same thing, we will write one more function for the deletion. And that is little bit tricky. Just try to understand that. Okay? So here I'll define one more function, that is the delete function. Okay? After the search, I'll define one more function. Def delete, and here I need to pass the value, which value I just want to delete. Okay, so self comma value. Okay, and same thing here I have to write certain conditions. Okay, first thing is value is less than the root or value is greater than the root. Two conditions I have. Okay, like I have to choose either I'll go in the left side or in the right side. Okay, so first thing is if value is less than self dot data, then what I will do here, I'll traverse complete left tree. Like three cases I'll make. Element can be leaf node, element can have at most one child, or element can have two child. element which we want to delete. Okay, so here the value which we want to delete. Okay, so first condition I am writing for leaf node. Okay, so here what I will do inside this, if value is less than the self.data, then we will reverse if self.be left until we have left element. Okay, and self.left, we create new left equals to self.left dot delete value. Okay, we will create the new left tree. We are deleting the element and we are assigning that element to the left. Else, one condition can be this, elif okay, value can be greater than self.data. Okay, then what I will write here, if self.write, okay, I'm going in the right side. So self.write equals to self.write dot delete value. Okay, these two conditions I'll take care. Okay, now this else part is very important. Actual working I'll do here. Like now I'll write three cases for the delete, either leaf node, either one child node or two child node. These are the conditions. I have to go in the left side, okay, and I have to go in the right side. I'm checking the conditions for the left and right. Okay, now in the else I'm writing one condition, if it is a leaf node, for the leaf node to be deleted. Okay, for this what can be possibilities? Self.left is none, means there is no left child and there is no right child. So I can write self.right is none. Okay, two things, and then what I will do, I'll return none. Elif, I don't need to shift anything, I'll just delete the element. Elif left subtree is none or right subtree is none. Like for the one child. Okay, elif self.left is none. Okay, then what I will do, I'll return left child is none, then I'll return the right child. Right child I'll replace at that point. You can imagine like this. This is element 30, like 60 I just want to remove. For the 60, left child is available. Okay, right child is empty. If right child is empty, then I'll return the left child. And if left child is empty, then I'll return the right child. Means I'm taking node having one child. So if right is empty, then I'll shift this left 52 in place of 60. Okay. Imagine this condition. Return self.write. Okay. Elif self.write is none. Then I'll return what happened. return self dot left. Clear? Now come to the interesting part. These are the conditions. Okay. Now I need to find out the minimum element of the right or either the maximum element of the left. Okay. So I have to define one more function for the find minimum. Okay. So I'll just getting the minimum value of right side. So minimum value of self dot right. Okay. Dot find min. I'm defining a function. I'll define it. Don't worry. Find min. Okay. This will give you the minimum value from the right side. And this minimum value we will set to the data. So self dot data that we want to delete. Like we want to put in the deleted node. So self dot data equals to min value. Okay. And then in the right side self dot right, okay, equals to self dot right dot delete min value. Let me explain in the diagram. Okay, and in this diagram okay, here I just want to delete an element like 25. Okay, I just want to delete 25, this element. For this, what I can do, I can put here 24 in place of 25. Here I'll put 24 in place of 25 and I'll eliminate this node. Okay, so same thing I'm doing here. How I can get the 24? 24 is minimum of right side. Minimum of right side is 24. Okay, and this 24 I'm assigning to the variable called min value. Min value equals to 24. And this 24 we will put like in a data, in place of data. This is my data, this is my current node. So self dot data equals to min value. I'll put the min value. Okay, and then what I will do, this element I have to delete. So this min value I have to delete. So self dot right, in the right side I have to delete the min value. So and new self dot right equals to self dot right dot delete min value. This is the thing I'm doing. Okay, clear? If you have any question in deletion, you can ask me, because this is little bit tricky. You have to find the minimum value from the right side, right child. So minimum value, we will write a function for finding the minimum value. So minimum value we got 24, that we have assigned inside a value variable min underscore value. And then what we are doing, this min value we are assigning to the self dot data, the data which we are deleting. So self dot data is this node. So in place of 25 we are putting 24. After putting the 24 we have to delete this 24 node. So in the right child, right subchild, okay, in the right node we have certain nodes. From those nodes we just want to delete only the 24. So what we are putting here, self dot right equals to self dot right dot delete minimum value. Okay, now we will see the code again. We have to write one more function here. Okay, this is the part, this will delete the values. Okay, here we will define one more function def find minimum, find min. Okay, and how we can find the min from the right side? So what we will write here, if self dot left is none. Okay, return self dot data. Otherwise we will return what? Self dot left dot find min. You can see this. If left child is none, okay, if left child is none, then we will return the value. Otherwise we will return left dot minimum. We will traverse this. Always minimum value in the left side. If you want to get the minimum value in the right side, then the minimum value in the right side is always left child. Like here, this is the right side. In the right side, we have elements 30 and 24. And from the right side, the minimum value at the left child, that is the 24. Okay? So that's why we have written this function. And we are using this function here. Okay? I hope you got it. Now let me run this function. We already built a tree. Okay? And from this tree, I just want to delete certain values. Like tree dot delete. I just want to delete 9. Okay? And after the deletion, I'll print the tree values. So same thing, I'll print in order traversal after deletion. After deletion. Okay? And there should be like 9 value won't print. It should not print 9. And you can see something wrong. Like this is my in order traversal 1, 4, 8, 9, 17 and 20 and 23 and 34. In order traversal after deletion. What happened? I'm creating a tree. Okay, let me build the tree again. Okay, and then I'll delete an element called 9. Let me run this. Something wrong. In the deletion code, I'll check it out. Okay, in the deletion code, we are deleting this. Okay, and then aleph self dot left dot delete, and for the right also we are doing the same thing. Okay, and in the else condition, okay, yes, I got it. I have to return here. Yes, return self. Otherwise what happens, it will give you the half output. Okay, let me run again. Now you can see the output is 1, 4, 8, 17, 20, 23 and 34. There is no 9. 9 is not available. Okay? Getting the things, guys? Can you please tell me how we can delete an element? This is the way you can delete an element in binary search tree. So we have performed 3 operations: searching, and we have created the binary search tree, then we done the traversing, and then we done the searching, and then we done the delete an element from this. Okay, you can try the another things, like here I have used find the minimum of right subtree. You can try find the maximum of left tree. Okay, you can replace this code. Find the maximum of another way to delete an element. Find the maximum of this right subtree. Means we can replace here, in place of 25, we can replace 13 also. You can give it a try. Okay? I hope you got everything, and if you have any doubt, like in the operations of binary search tree, you can ask me. Otherwise, I'll try to cover each and everything in binary search tree in respect of implementation part. Like in order I told you, you can try pre-order and post-order traversal. Okay, simple, that are the simple. And deletion you can try in the another way, that is the finding the maximum of left child. Okay, you can give it a try. Finding maximum of left subtree. Okay. I think this is enough. You guys can try after the class, write the code by yourself. You can take the reference. We will provide the reference notes in the description of this video, so you can see the reference and then you can write code by yourself. Okay, then only you get the clear idea about the implementation of binary search tree. And binary search tree is used in order traversal always gives you the tree values in sorted order. So its complexity is log n. Yesterday we have seen the complexity also, like how much time it's taking for the searching, deleting, all these things. And you clearly know what is the binary tree and what difference between the binary tree and binary search tree. Okay, so no more questions. Okay, thank you so much, and we'll see you in the next class.